I'd like to present a few slides here on basic vehicle dynamics. I'm going to explain a more holistic approach, the basic things that we should kind of have in mind when talking about vehicle dynamics. I've read various things. It's easy to get stuck in the details. It's a huge subject when we talk about vehicle dynamics. And I'm a mechanical engineer. I have like a passion for cars. I'm not a race driver. I haven't been in a team, but I'm more kind of someone who looks into these things. And I'm going to make a small presentation here of the things that I've seen in my life and my understanding of this issue. The first thing is when we are in steady state turning. What I'm trying to show here with these formulas is that depending on the center of gravity, of course, the theta, or the slip angles, right, will be greater. And so a car that has the center of gravity in the center will usually have a more neutral steer. And a car that has the center of gravity towards the front will have a more understeer type condition. However, what I'm showing in the right hand side, when I'm saying N left percentage and right percentage, is how the cornering force is distributed between the left and the right tire. For that, it is important to note the stiffness of each axle. So if you have a stiffer roll bar on the rear axle, then the rear axle will slide sooner. So you can adjust the attitude of the car from understeer to oversteer using the roll bars, or often using, I had a very good, very fast car setup by stiffening the rear, stiffening a lot the rear dampers. So I had the rear dampers very stiff. So turning into the turn, it was a front wheel drive car. So when I turned into the turn, as the car rolled, right, there was a bigger weight transfer in the back. So the weight transfer in the back, because the dampers were so stiff, was bigger, and it made the rear slide a bit going into the turn. And this was a very fast setup for a front-wheel drive car. So it's the same principle, but I achieved it with dampers, which means that you had that oversteer going into the corner when you applied the cornering force, and it made the front end ripple a little more going into the corner. There's a whole bunch of other ways to do it, stiffer springs. So this is one thing you might want to look into when setting up your vehicle when you change the springs. Aftermarket springs, you usually have stiffer springs in the back, and it will change the attitude of a front-wheel drive car towards more of an oversteer setup. And that will make you significantly faster. And if you have the ESP or VSC, whatever, you have a stability program on your car, it's not really that dangerous because the stability will cut in. So that's one thing that's very important in regards to the attitude. The other thing that we look into is weight transfer. I have here this vehicle. What we need to remember about weight transfer is that obviously the lighter axle will slide sooner. But the weight transfer affects the axle that is lighter, that's far away from the center of mass, that is lighter anyway, even in a static situation. So in this picture here, where the center of mass is towards the front, you have a bigger problem with weight transfer when braking. So front-wheel drive cars, braking into corners, you will feel they are a bit unstable. Porsches, for example, would be great braking into corners because the weight is on the rear. You won't have that problem with the weight transfer to the front. You'll have the weight transfer to the front and it will make the car very stable. But Porsches have a big problem because the front axle is light when you get on the power mid-corner. So when you get on the power mid-corner, you better be sure that the car has settled into a neutral or oversteer situation, because it will understeer if you're cornering close to the limits for the Porsche 911 or these cars with the engines hung over the rear of the wheel. So that will cause the car to understeer mid-corner. When the moment you get on the gas and transfer the weight off the front, causes the car to understeer. And that can set up a difficult dynamic situation for which Porsches are very renowned. The same thing for mid-engine cars, which have a rear weight bias. So that's what I'm showing here. So when there is a transfer, the front, there'll be a 30% difference, for example. The rear, it'll be 50% almost difference. It's most pronounced on the lighter axles, and it's more sloppy on the lighter axle. Here I'm showing the grip circle, right? Another way to show how understeer and oversteer is to show how the grip circle is bigger or smaller depending on the dynamic balance of the vehicle, whether it's accelerating or decelerating. And the grip circle means that about, right, the traction is the same for all directions. So you can, it's the vector, the vector, the addition of the vector of the longitudinal and lateral acceleration cannot go outside the grip circle. So when you are braking, for example, your front grip circle will become larger because you have more weight on the front, and vice versa. Now about the wheelbase and the inertia. The wheelbase and inertia, this was something that my professor in university talked a lot about, because this is kind of an American concept. Americans have a different way often of looking at things. They kind of get stuck on one thing. I think this was coming from an American perspective. Yeah. If you don't have any overhangs over the wheels, right, the car will be more agile, because the wheel acts in regards to the center of mass, right? Has a moment, a force moment in regards to the center of mass. So the farther away the wheels are from the center of mass, the more agile the car will be. But our professor was very interested in what he called the point of percussion. The point of percussion means that reactions from one wheelbase are not transferred to the other one. I show here with the rod that's hanged. So you imagine that the rod is hanged at the one wheelbase and we hit it at the other wheelbase, and you don't want the rod to move at the other wheelbase. So what that means is that any reaction at the other wheelbase, at one wheelbase, is not transferred to to the other one if you are at a point of percussion. This is very good for comfort, and it's also good if the rear wheels are at the rear point of percussion. There's a significant overhang, and the rear wheels are close to the point of percussion. This car is good for drifting because as the car slides and that slide stops, it will not transfer to the front wheels. It will not transfer a reaction to the front wheels. So you can just correct and keep on going and then slide the other way or whatever. If the rear wheels are at the end of the car, at the corner of the car, when that slide stops, it will transfer a reaction and have the front snap out. So the point of percussion logic has this mentality. Suspension. Part of a suspension, the only people that I know of cars that have a good soft suspension, really good soft suspension, are the Renault line of cars where they have the rear axle with the passive four-wheel steering. So they have a semi-rigid rear axle with passive four-wheel steering, and that works very well to neutralize the understeer that's common in front-wheel drive cars. Almost all other cars, they have problems when the suspension is soft. They have bump steers, there's weight transfer, there's all kinds of things you need to do with the geometry of the suspension, and I don't think anybody really gets it right. They all get stuck on details, and they think this and that. Something that's been said in a magazine about vehicle dynamics, this was a magazine for engineers, is about getting the weight of the steering wheel correct so the driver is synchronized, the driver input, right? When the driver wants to drive fast, the input of the steering wheel is synchronized with the rate of rotation of the vehicle. Oh, that's a good concept. There's lean oversteer, right? So when there's lean oversteer and there's a lot of with the bump stops. So a lot of people are now started playing with the bump stops. When the car leans a lot, so you are close to the limit, they will have the rear bump stops. Remember what we said in the first slide with the weight transfer. They'll have the rear bump stops stop first, and that will transfer so as the car has a tendency to understeer, to make it more stable, more easy to drive. But when you're really at the limit, the rear bump stops will engage first and transfer the car towards oversteer, kind of like in lean oversteer in multi-link suspensions. But all of this stuff, the problem with soft suspension is it can work when you know what to expect. For example, in rally driving, yes, it works. But rally driving, you'll see rally drivers, they're constantly in their minds, they're constantly aware of the weight. It's all about taking care of the weight, and you have to constantly know where the weight is. So they'll come out of a corner and they'll wag the weight this way, and then that way, and go into the next corner. So you can see that they'll go this, in. That doesn't really work when you have to make evasive maneuvers against something that you can't predict, a dog jumping out, a little kid or something. So a soft suspension is not really good in that sense. That said, some people do get it right. and it's a very, very complex issue. Steering field and geometry. Yeah, there's, yeah, again, I say here it's very important how to connect the wheel input to the vehicle response. Is very important. With the roll centers, also something important is the roll centers of the of the of the suspension, and what height is the roll center, and how the vehicle settles when it turns into the corner. However, for me and my experience with my vehicles, after I put a lowering kit and a stiffer dampers on them, uh, it just doesn't really make any. It's all a little bit everything that we say about geometry, suspension, roll centers, all that stuff is trying to solve a problem that is solved once you stiffen up the suspension and you get a better response. You fix everything. So you can play with the geometry all you want, but you're never going to have the performance that you're going to have with a stiff suspension, and you really don't have that much worse of comfort. So for me, that is my advice. And I've looked at. I'm going to show now the the plots from various tracks where you have the plot of the horsepower per ton and the vehicles, and the difference between the well setup is about 7%, but that's about the difference you get also by lowering your car and stiffening the suspension. So if you lower your car and you stiffen the suspension, you get all the performance that you would get by having a very good setup, a very good geometry, a very good roll centers, very good. All of that is just a lot of discussion to fix a jelly belly, basically suspension. That is basically wrong. You're trying to fix something that is wrong because of the weight transfer. The weight transfer causes a lot of problems. So you're trying to control it with roll centers, you're trying to control it with geometry, you're trying to control it with all kinds of different techniques. But if you really want performance, you have to lower the car, stiffen the dampers, stiffen the springs, stiffen the roll bars, get rid of the weight transfer altogether, except for rallying, obviously, where you're on the dirt and the bumps and the rough stuff. From my experience on mountain roads that I drive, these mountain roads, and I have times a motorcycle, and from these plots that I've done between horsepower per ton, and motorcycles generally behave like well set up cars. And motorcycles, because the forces are on the axis of the axis of the reaction from the road, you don't have to go so stiff with the suspension, and they behave like well set up cars in practical conditions on the road. At least that's what my data suggests. So they behave like a well set, like a lowered car fit with stiff springs and stiff dampers.